Now we will see some undecidable problems about Turing machine. We will see just the basic of this, and I have left one theorem, means I have mentioned the theorem here. Still the proof is there in your study material attached to this lecture, and you can find a formal proof there. And since we have covered many proofs of the same kind, so you can do it of your own. Still I have kept the formal proof in the study material. And after learning this, we will move to a important problem or important theorem, that is Rice theorem, and we have proved the Rice theorem taking the help of this universal Turing machine, which we have learned in our previous class. So before directly moving to the topic, we will see one important thing, that how one problem can be reduced to other, means what is the benefit of reducing one problem to another problem. Okay, so say there will be many situations in real life. If we have to prove, okay, that you prove that this problem is undecidable, right? That means we cannot construct any Turing machine that is guaranteed to get halt, right, for this kind of problem, or for acceptance of the kind of languages which this problem is going to generate. So always, without directly moving to that problem to prove that that is undecidable, we can take a shortcut of it. What is the shortcut? Say we are having one problem which we have already proved to be undecidable. We know that this problem is undecidable. We have proved that. Now if we can reduce this new problem, means when the problem in which we are working on now, if we can map this particular problem to the previous problem which we have already proved to be undecidable, then we can conclude that this is undecidable as well, right? Since we can map this problem according to the previous problem, and we have already proved that the previous problem is an undecidable problem, then we can easily come to the conclusion that okay, this is also undecidable. Now there will be a question that whether we are going to pick up every instance of my new problem and we have to map each and every instance to the previous problem. Definitely not. It is not possible, because it will consume so much of time. So what we are going to do, if we can map at least any or one or two instances, or if more than say 2 to 3 instances with the previous problem, and can prove that we can map it, then we can say okay, this is not going to get halt as well, right? If it is not halting for one or two instances, that means at the end of the day this machine will not halt for all the choices. That's why it will be definitely undecidable. So if we can prove, if we can map 2 to 3 instances, if it is for this, if it holds for this non-halting condition for 2 to 3 instances, so it will work for the overall thing, right? So ultimately it will be an undecidable machine or undecidable problem, right? Now here what is there, suppose we are having a problem P1 which is undecidable, and we are having a new problem say P2. So what we are doing here, see, we had P1's instances with us, and we are using a construct, means using that construct we are going to map the instances of P1, means my existing instances, to the new instances of the problem, of new problems instances, that is P2's instances. And we know that for this instance my P1 can decide to yes, or for this instance my P1 can decide as no, right? Now if we have successfully we can map, that means for the P2 it will work in the same manner. That means if we have mapped some instances of P2 with the P1. When we fed that instance to my decide, this diamond box decide, it will act accordingly, right? So my the conversion is fine, that means it is working in a correct fashion. Now when we are how we are going to do it, say we are given with an instance of P1 that is given a string W that may or may not be in language of P1. Now apply the construction algorithm to produce string X. Now we will ask, what is the construction algorithm? So we cannot provide you with a definite construction algorithm. It is totally dependent on which problem you are working on. How we are going to map one problem to another, that is completely depending on which problem you are working on. There cannot be any stereotype algorithm for the conversion. So only way out, that is you can try to map that this instance of this problem can be mapped to this kind of instances of the other problem. So if we have to tell it in a more formal way, that how we are going to do, say we are having a string named W in P1 which may or may not be in P1, that is we have to decide that we are feeding a string W to my P1 that may be in the language or may not be in the language, right? So it will come up with the conclusion. Now we will, using the construction algorithm, we will produce another string X. Now what X is going to do? We are going to test X, right? And we have to wait that whether the same results are coming or not. That means what? If W is in P1, then X should be in P2. If W is not in P1, X should not be in P2, right? Now either way it says the truth about W, right? Same thing. Since we assume that no algorithm to decide membership of a string in P1 exists, we have proof by contradiction that the hypothesized decision algorithm for P2 does not exist. Since we have converted the instances of P2 to a string W of P1 which we use for making the decision, means the working of P2 is now totally following the working of P1. So since we have already proved that P1 is undecidable, with already proof means we have picked up such a problem which has been proved to be undecidable. So without directly proving that P2 to undecidable means it would follow a different approach. Totally we have to think of a different approach. So we have successfully reduced my P2 to P1 and can directly come to the conclusion, since P1 was undecidable, so P2 is undecidable as well. Now why we are into this topic? We will use this same theory underlying to prove that some undecidable problems about Turing machine. If you are given with any undecidable, say you are given with a problem that you have of Turing machine, you have to prove that this is undecidable. So if you have priorly proved some problems of Turing machine to be undecidable, for any new problem you can map that new problem to some existing undecidable properties of Turing machine, and you will be able to come to the conclusion whether that is undecidable or not without reconstructing the new problem, right? So here the same fashion is we are going to follow. See what it is doing here. If you can see in the diagram, there are some instances of P1 in the first circle which is having an answer yes, and we are mapping the P2 yes portion with the yes portion of this P1, and same for the no portion, right? Now you can see in the diagram that whether we are covering the total yes portion of P2 with the total yes portion of P1. No, you can see that there is a small circle in the second large circle marked as yes, means yes is the total block, but we have picked up few instances from the total block of yes, and we have successfully mapped to the yes part of the P1. That means if it holds for this much of value, it is true for all the values, okay? And similarly for the no portion as well. Okay. Now formally, a reduction from P1 to P2 is a Turing machine that takes an instance of P1 written on its step and halts with an instance of P2 on its step. If we have to define it theoretically or rather formally, that means what? If we have means this reduction process, in case of reduction process, if we have if we have taken any instance of P1 I have written on my tape, and when it is going to fed, means when we have fed this tape to my Turing machine and it is halting with an instance from P2, that means it is doing what? It is acting similarly as that of P1, right? But in practice, what we are going to do, in practice you cannot construct any tape in Turing machine. We have to means we have to proceed in a programmatic approach. We have to construct computer programs, right? So what we will do here, we will pick up an instance of P1 and produce an output of P2. That means from P1 we are converting something to P2, right? Means we are using P1 to cultivate something for P2. So this thing, if we say in the language of Turing machine, that means for an instance of P1 in a tape of a Turing machine, an instance of P2 is going to halt, right? That means it may go to accepted state. We are not talking of those accepted state concept, but my Turing machine will halt. That means it will come up with an output, right? Whether it has accepted the string or it has not accepted, but it will come up with a result. Okay. Now the equivalence of Turing machines and computer programs allows us to describe the reduction by either means. So if you want to go to much, if you want to have a deeper knowledge on how a Turing machine and a computer works similarly, you can again consult the book of Hopcroft. There you will see a Hello World program has been there, is mentioned there, and it has been proven that how it is a Turing machine can be equivalent to a computer program. Okay, fine. Here now this is the theorem where if there is a reduction from P1 to P2, then P1 is undecidable and so P2, right? So if P1 is undecidable, then P2 is also undecidable. So we have seen the proof informally, but if you have to write the proof formally, you may follow the study material. There I have mentioned the proof formally. And now if P1 is non-recursively enumerable, so P2 is also, right? Now why P1 is non-recursively enumerable? Because here we are coming to the conclusion that P1 is undecidable. That means my Turing machine is definitely going to halt. So this is definitely not non-recursive, it is not a recursively enumerable language, because recursively enumerable language does not guarantee halting always. Okay, there are some situations where my Turing machine will keep on processing and it will never halt. It will keep on running for the lifetime, right? So it will be under the the category of non-recursively enumerable. But do not think that we are focusing that this is recursive. Okay, it may be recursive, may not be recursive. That proof you can see from the study material, but it will be definitely, since it will halt, it will come up with a result. It cannot be recursively enumerable language. Okay, now let us move to this important topic of Rice theorem. So we will use one more property here of the undecidability of the universal Turing machine. That proof I told you to learn it from the book of Hopcroft. So you can see the proof, but if you even not going formally into the proof, so we know that if we can use that property only here, we will be able to learn the Rice theorem. So what Rice theorem is stating, every non-trivial property of the recursively enumerable languages is undecidable. Now what is a non-trivial property? Just look at the footnote of the slide. A property is trivial if it is either empty, that is satisfied by no language at all, or is all recursively enumerable languages, right? That means all those properties which either come up with an empty language, that is, it is not accepting any language, or else whatever languages it is accepting, all falls under the category of recursively enumerable language. If it is not, then it is called non-trivial property of the RE language. Okay. Now the properties which are non-trivial, those are undecidable. We will pick up this non-trivial property in a variable called P, and we will try to map the total thing using a universal Turing machine. So let us directly go to the proof. So what proof is saying? Here we are assuming P to be a non-trivial property of the recursively enumerable language. Now we are assuming to begin that this phi, the empty language, is not in P. So we are just assuming it beforehand, because since it is a non-trivial property, it is not going to be empty, right? If it is an empty, that is, if this property is not satisfied by any language, then it will fall under the category of trivial, right? So since it is non-trivial, we are assuming this as the initiation of the proof, that we are assuming this my empty language phi is not in P. Okay, now later on we will prove this to be a different case. We will see that. Now since P is non-trivial, there must be some non-empty language L that is in P, right? So there, since it is non-empty, so there should be some language in P, and we are assuming that to be L. That language, means this non-trivial language, is to be L, which is getting accepted by a Turing machine named ML. Okay, now let us see how we are going to proceed. Now what we are going to do, the language acceptance is by non-trivial property, say L of P, right? We are assuming it as to be L of P, and we are trying to reduce my universal language, that is L of U, to L of P. Now thus proving that L of P is undecidable, since LU is undecidable. So what I was talking of, to learn the proof from for the universal language that LU is undecidable from the book of Hopcroft, there you will see that it has been proved formally that why LU is undecidable. Okay, and for now we will just assume that we will just keep in mind that it is a proved statement that LU is undecidable. So we will try to prove that LP is undecidable as well, because we are reducing LP to LU. So if we can reduce one of the new problem to an existing one, so by the property of reduction we can prove that, we can say that this is also undecidable. Okay, now see how it is the sketch is working on. The algorithm to perform the reduction takes an input of a pair like MW and produces a Turing machine M dashed. Here we are going to produce a Turing machine M dashed. How it is working, you can see there are two different inputs. One input, that is W to M, another input X to ML, right? So these two machines are there, and it will this total concept, or this total, the combination of two machines will fall under one machine, that is M dashed. Okay, so why we are taking two machines, we will see. What it is saying, that here L of M dashed is phi if M does not accept W, and L of M dashed is L if M accepts W, right? Why? Because you can see here, if M is not accepting anything, right, so it will do what? If W is fed to M, right, and my M is not accepting it, so what it is a part of M dashed, so it will be phi, right, if it does not accept. And if it accepts, that is if my M accepts W, then it will accept the language of M, right? Now here, how to construct it? Since there are two different machines, we can use two-tape Turing machine to represent it. One tape is doing what? One tape is going to simulate M on W, and the other tape will just mimic this ML, right? One tape is for M, that is going to simulate the W part, that is the input, faded input, right? Remember that the algorithm performing the reduction is given M and W as input and can use this input in designing the transitions of M dashed. Right, so we know that this M comma W format, if we are given it any tape, that M comma W format, we can reduce it using the binary string format. We can design the transitions of M dashed, right? We can design it following that coding pattern of Turing machine which we have learned so far. Now thus the simulation of M on W is built into M dash. The latter TM does not have to read the transitions of M on a tape of its own. Since we are simulating this part, so it will be written to one of the tape of, means whatever M is having with it. Say W is fed to M. Now how this M comma W is working, the total transition functions will be written to one of the tape of M dashed, so it will work fine. It can work fine. It has just copied it. Now the other tape will do what? The other tape of M dashed is used to simulate ML, which one is the second machine, on the input X to M dashed. So if necessary, this is necessary, we will use the second tape. Now again, the transitions of ML are known to the reduction algorithm, and it can be built into the transition of M dash. So again, it will follow that M comma W pattern, and it can mimic all the transitions of ML and can write it on its second tape, right? Now how it is going to work, means how it will work. See, simulate M on input W. Note that W is not the input to M dashed. Rather, M dashed writes M and W onto one of its step and simulates the universal TMU on that pair. Since we are using this M comma W, and before starting this Rice theorem, or at the beginning of this Rice theorem, we have already told you that this M comma W, we are mimicking the working of a universal Turing machine, right? So it has already simulated the total functioning of universal Turing machine into one of its steps. Now if the situation is like this, if M does not accept W, then M dashed does nothing else. M dash never accepts its own input X, so L M dash equals to 5, right? Why? Because if this universal Turing machine is not accepting W, then M will do what? M will, means it cannot accept W as well, means it cannot work anymore. It will be at the halted state. So this input where the X is been fed, that will not work at all. Why it will not work at all? If you can see the diagram, we have fed W to M, and we have fed its accept, means when W is going to get accept, that will make my another machine ML work, right? If W is not going to be accepted by M, then we cannot make ML start working. So whatever the input you give to ML, that X input, it is not going to work on it, right? So whenever W is not accepted accepted by M, then what will happen? My language will be empty. So we have assumed that this non-trivial property to be that M dashed is not going to accept my empty language, but we have proved ourselves false, right? Here in this situation, it will accept the empty language. That means what? Since it's a non-trivial, we are going to prove that it's a non-trivial property. So is this a code for LP? Means the non-trivial property? No, because the property of, or the criteria of a non-trivial property is such that it is not going to accept any empty language. So here m dashed fails and it cannot cover the property of LP, okay, for this situation. Now if the situation is otherwise, that if my m accepts w, then what will happen? And m dash begins simulating ml on its own input x, because since it has got an accepted result, so my ml will start working now. Now it will the x can be fed to it and it can work accordingly. Now m dash will accept exactly the language L, right? Because the language L means the language generated by this ML, machine ML, right? So since it can work, means x has been fed to ML, so it may either accept or reject based on whether this x string falls under the language which ML can accept or not, right? So since L is in P, the code for m dash t is LP. Here it is working fine, but for the previous case it was not working correctly, right? Now constructing m dash from m and w can be carried out by an algorithm, since this algorithm turns to be m comma w into an m dashed that is in LP if and only if mw is in LU, right? So if mw is in LU, that means if w gets accepted by m, then only this LP works fine, right? Then you can say that this my m dash is mimicking LP, or it is a class of LP. That means it is satisfying a non-trivial property. If w is not getting accepted by m, that what will happen? Then it will accept the empty language. So that is not the property which we were waiting for, right? The LP cannot accept any empty language, but if w is not getting accepted by m, then it is going to accept empty language. So if and only if this universal Turing machine works fine, if it accepts only, then it will work, then my LP is going to work fine. So now you can see that we have successfully mapped LP to LU. So based on the whatever LU is doing, we can predict what LP is going to do. So since we have already proved that my universal Turing machine is, the language acceptance by universal Turing machine is undecidable, so we can, using the property of reduction, since we have reduced LP using LU, we can prove that P is undecidable also, okay? So this is the end of today's class. In the next class we are going to learn one more topic from this module, that will be our last topic, that is post correspondence problem, okay? We will see what is it, and it's a very important topic, we have to cover it. Thank you.